So onward with our 30,000 foot view, and we are on to the citric acid cycle. So again, that's a number 3. If we go back to our large sort of overview here, we are at sort of the third stage here. Now remember, we're learning about this fuel metabolism process from a very glucose focused sort of standpoint. So we started with glycolysis to generate pyruvate from glucose. Pyruvate undergoes dehydrogenation chemistry, eliminating CO2 with pyruvate dehydrogenase. And then we get to this important branch point metabolite called acetyl-CoA. Now, why acetyl-CoA is important is any fuel can be made into acetyl-CoA. Carbohydrates can be made into acetyl-CoA. When we talk about fat metabolism, fatty acids only make acetyl-CoA as an initial branch point metabolite. And then many amino acids can be converted into acetyl-CoA. Okay, we're going to call those ketogenic amino acids. But I want you to think of this like a funnel approach. Is once we get to acetyl-CoA, it doesn't matter sort of where we got that from, what fuel source. Ultimately, if we are in a need state, acetyl-CoA is going to be going into the citric acid cycle, and we are going to fully squeeze all the energy out of that sponge. Remember our sponge analogy. We've got a sponge where the makeup of the sponge is really our carbon atoms. They're held together by electrons, which is the water in this analogy. And so when we go through fuel metabolism, essentially what we want to be doing is squeezing all of the water out of that sponge. We're harvesting that water, those electrons, as reduced cofactors like NADH and FADH2, and eventually our sponge is cut up into little individual carbon pieces, which are eliminated as carbon dioxide. So this is a really important process for doing the bulk of that oxidation chemistry to generate reduced cofactors and then liberating those carbon atoms as CO2. Okay, so let's get into the nuts and bolts then of what happens in the citric acid cycle. Like we've done with our other sort of pathways, let's start and remind ourselves what the net reaction is. Again, this is not something that has the right stoichiometry or things like that, but I want you to know what do we start with and what do we end with. So the citric acid cycle starts with acetyl-CoA. And the 4 products that I want you to know that are made is those carbon atoms are eliminated as CO2. We generate both reduced cofactors, NADH and FADH2. I'm going to move myself over just a little bit here. And then importantly, we do start to generate what we'll refer to as like primary currency, but it's not ATP directly, it's GTP. So again, metabolites that we have here is we start with the branch point metabolite acetyl-CoA. All of those carbon atoms are converted into CO2. We've got some alternative currencies as the B vitamins NADH and FADH2, again, vitamin B3 and B2 respectively, used to make those. And then we start getting at some primary currency, GTP. Like we've talked about with other processes, I want you to know where this occurs, whether it's aerobic or anaerobic, and how many steps that there are. So this is a mitochondrial process. And really, anytime we are going to talk about for this 30,000 foot view, anytime we're doing something in the mitochondria, we're going to define it as aerobic, right? We're not allowed to do biochemistry in the mitochondria unless we have oxygen around. And importantly, this is 8 steps that we're going to consider. So just like we did with glycolysis, we sort of broke it up into 2 halves. The same is going to be true here for the citric acid cycle. We're going to have a stage 1 and a stage 2. Now, because this is a cyclic process, there's going to be some other pieces that we need to sort of consider here, but I want you to envision the citric acid cycle like a clock, and we're really going to be talking about the 12 to 6 o'clock and then the 6 to 12 o'clock sort of time frames. So there are these first reactions here. I'm going to highlight them in green. This is stage 1. So for these processes, just like we did for glycolysis, I'm going to highlight the things that I need you to know. So I'm also going to relate this to things that we talked about for enzyme catalysis. Remember, we talked about the 3 things that need to happen for enzyme catalysis. We need to do chemistry on the substrate, we need to use all our reagents, and we need to return our enzyme's active site to its proper state. Right? So we're going to use that same sort of umbrella here, understanding that there's multiple enzymes that are part of this 8-step process, but we're going to use that same philosophy and say what happens in stage 1 where we generate carbon dioxide. So again, this is carbon dioxide generation. That's the purpose of stage 1. So let's highlight sort of where we see that, so we can see that CO2 generation. After these 2 steps, we'll go into the details of how that happens next semester. But I want you to think about that this first half of the citric acid cycle really accomplishes the first half of what we think about with enzyme chemistry. We do chemistry on the substrate. Remember, if the purpose of this pathway, which is really multiple steps, is to take the carbon atoms that are in acetyl-CoA and convert them to carbon atoms that are CO2, we've done that chemistry. We've generated those products. So we've done chemistry on the substrate. We've generated our CO2, right? So the other thing that we're going to think about is the fact that we also have generated a good bit of our alternative energy, that NADH that we have here. But remember, the second stage, the second act, if you will, when we did all of those enzyme active sites, were to use all the reagents and, importantly, return the enzyme to its active state. Okay, we needed to regenerate that enzyme active site. So the second stage of this process is really going to be thinking about that. So I'm going to highlight that in blue here. So these steps that we have highlighted here, sort of in the 6 o'clock to 12 o'clock stage of our clock, that's stage 2. And what I want you to think about with stage 2 is we're not returning an individual enzyme to its active state. We're returning a pathway to its active state. And how this pathway needs to continue, remember, this is a cyclic process. Look here, there's this molecule called oxaloacetate. Oxaloacetate is used in the first step and then regenerated in the last. By definition, that's what a catalyst does. A catalyst is something that's used in a process and accelerates its reaction rate, but is also regenerated at the end. So oxaloacetate is really a catalyst for the citric acid cycle. So just like we have amino acid side chains that help to catalyze enzyme active sites, we need to make sure that we regenerate those in their active state. So we need to regenerate this active molecule, this catalyst, to sort of continue glycolysis. So let's put that down in words here. What really happens in stage 2 is we need to return our pathway to the active state. So return our pathway to the active state. And what that really means is we need to regenerate oxaloacetate. So we need to regenerate oxaloacetate. And from now on, we'll probably abbreviate it OAA, reminding you, keep up on your alphabet soup. There's so many acronyms that we have here. You want to be able to see all of these acronyms and know what they are. Okay, so we do have OAA that we need to regenerate. And highlighting, just because we mentioned it, this is a catalyst for this process. And by definition, a catalyst is consumed in maybe the first step or early steps of a reaction. It makes the reaction faster, but it's regenerated, and that's sort of the key that we have here. Let's just highlight a couple of the other things that do happen in sort of this second stage, as we do generate some more of our reduced cofactors that we're going to be able to cache in the electron transport chain for energy. And we do have a little primary currency that we make. Now, it's not ATP, it's GTP, but GTP and ATP are sort of net energy equivalent. They're both worth that 30.5 kilojoules per mole. So the last thing to sort of map on here, and we sort of talked about this with pyruvate dehydrogenase chemistry, we talked about the fates of pyruvate. What you do with pyruvate largely has to do with whether you are in an aerobic or anaerobic state. Aerobic state, you get to go into the mitochondria. Pyruvate is metabolized by pyruvate dehydrogenase chemistry. If you are in an anaerobic state, the only option you have are fermentative pathways. And again, for us, that would be homolactic fermentation. So we're going to do that sort of same decision process and say, well, what are the fates of acetyl-CoA? And truly, the fates for acetyl-CoA that we're going to do in this 30,000-foot view are really to say whether you are in a need state or a fed state is going to determine sort of what happens to acetyl-CoA. So let's talk about the fate of acetyl-CoA. So the fate of acetyl-CoA is largely dependent, and I'm going to move my stuff here, give myself a little bit more room. So the fate of acetyl-CoA is really dependent on, I'm not able to select this here, on whether you are in a need state or a fed state. There we go. Now I've got some room. Okay. So let's highlight that these two options are, we've got a need state and we've got a fed state. And remember how we've defined need state and fed state. Need state we can say is either glucose or energy needs, okay, whether you've got low blood sugar or you need energy, okay, that we're defining that as a need state. And then fed state is just excess fuel. Okay, so let's sort of map that in here. Fed state is excess fuel, and need state is going to be energy, or it might be that you need glucose. And that's going to come into play later on when we talk about why we might have gluconeogenesis happening when we are under a need state. But at the end of the day, if you are in a need state, acetyl-CoA is going to go to the citric acid cycle. Okay? Hopefully you remember just a little piece here. If we are in a need state, acetyl-CoA cannot fix low blood sugar. Remember, we cannot convert acetyl-CoA into pyruvate, which means we cannot convert acetyl-CoA into glucose, okay? So in general, if you're in a need state, you're going to be metabolizing that acetyl-CoA as a fuel, and you're going to be generating carbon dioxide and lots of energy molecules. If you're in a fed state, what you're going to be able to do is you are going to synthesize those acetyl-CoA. You're going to hook those acetyl-CoA molecules together into fatty acids. And then those fatty acids are going to be assembled into triglycerides, and then ultimately you are going to be storing those in adipose tissue. Okay, so another one of these situations where what we do with this branch point metabolite is also ultimately determined by what state you're in. Okay, and for the fate of acetyl-CoA, it's ultimately determined by whether you are in a need state or a fed state.